Hi, everybody. Welcome back to the Astro Imaging channel. We've got a sparse crew bringing you the show tonight. Molly's down with Larry Groom and Okie Tex down in Kenton, and they're getting ready to take some imaging rigs of Okie Tex Part 2. And they say they're going to do a much better job of it because they've got a much better crew than when I did it last year. So we'll see how they do when they get back. And they're going to have a show for us sometime, I think in November. And right now we're scheduled all the way through January, but we could still use some more people. So go ahead and sign up. I'm coming to you from Goat Mountain. It's Goat Mountain out that way someplace on an iPhone because I've been working all day repairing the facility. This is our club observing facility. Tonight, we got a pretty interesting show for you. For about the last 2 or 3 months, we've been taking pictures. You all have been taking pictures of the heart of the galaxy, you know, down near Sagittarius and all that other stuff, all the really cool big gas clouds and globulars and, well, just all that stuff down there. And Arno has put them together into a video, and Terry's going to be playing that in a minute or two. And then we're going to have 2 tutorials. And the 2 tutorials are going to be about, one of them is called Diverse Data. And that's for all of you who, you know, you use different scopes or you try to do different things with your scopes, or you make a mistake and you forget to set one of your settings right. And you say, so how can I use this data? Well, we've got a tutorial to address that particular question. And then Master Processor. Eric Cole's going to take us out to the James Webb Space Telescope, and he's figured out ways that he can process the data and get some beautiful, I think he's going on Eta Carina, and he gets beautiful data in like 10 minutes. He can process this to perfection. So we're going to be looking at that towards the end of the show. Next week, Warwick Anderson is going to be with us. Warwick is going to be telling us about how to get started in astrophotography in 10 easy steps. Terry's handling the controls today, and we're going to ask Terry to start off the show by showing us, hey, Arno, your Australian mate down there, is the guy who puts this together. Thank you, Arno. Terry, why don't you take that away and show us what's at the heart of our galaxy?
Terry?
That's 6 minutes, 4 minutes, 6 minutes. Is it playing?
It is playing.
It's good? Okay, we're good. Good job, Terry. And nobody can hear us, right?
Yeah, there is audio.
Close to finished so that I can. Ready?
Yeah, that was quite a
Anyway,
delay.
so-
It just started just now.
I just wanted to make sure we could hear the audio. It is
Yeah,
playing.
I
on
just
YouTube.
listened to it for a moment.
something happens to my audio, Eric, be ready to go with your
Yeah.
presentation.
The meeting audio is also being podcast, I think.
We should get ourselves.
Thank you, guys. That was a great video from Arno. We're back. Can you guys hear me?
Yes, we can. Are we ready to go back?
We're ready to go back. So
program?
Yep, we are.
Okay. Several of us are kind of remote right now, so it's kind of hard to keep track of everything that's going on. You know, we will be showing Arno's movie, The Heart of the Galaxy, as a separate YouTube post without our voices a little bit later. So that will be posted and you can get a hold of that. There's a whole nother series of programs that are coming out of the Astro Imaging channel lately that you may or may not have noticed. We want you to be aware that there is a new resource where, well, I'm not going to tell you about it all. I'm going to have the guy who's kind of the force behind all that. Patrick, can you tell us a little bit about what's happening with the tutorials and the shorts and all that other stuff?
I sure can, Alex. Well, thank you. Good evening, everyone. And, you know, as Alex mentioned, we have been putting together the what we're calling the TAIC shorts, which is basically just a series of smaller segments, tutorial type videos. And as Alex mentioned, tonight's episode is really a compilation of a few different smaller, shorter segments. And so that's kind of a nice tie-in to what we've been trying to do with the TAIC shorts in general. And certainly anyone who's been watching the Astro Imaging channel for any length of time knows that there's quite a bit of content. The library is very deep. The channel's actually been going since 2014. And one of the really neat things about the Astro Imaging channel is that we cover topics in depth. That's really what sets TAIC apart, I think, from a lot of other YouTube channels, is the fact that we don't just sort of scratch the surface of topics, but really try to dig into them, and that's great. But that said, sometimes there are certain things that you might want to see again, or just a portion of a video that's how-to of a different, certain types of processing or equipment setup or whatever it might be. So what we've been what we've been doing is trying to go back through the library and pulling out some of those segments that have been more popular, that seem more helpful, and then making those into a shorter segment, so that that way, if somebody thinks, oh well, didn't Tim do a video on enhancing Hubble palette with HA data or whatever it might be, and then having not necessarily have to go back through and rewatch the entire episode, but to be able to go back and have it at your fingertips, those shorter segments. So that's what we've been trying to do. And as I mentioned, one of the challenges just with the depth of information that we have, the library that we have, is just trying to identify those, find the episodes or segments that are still pertinent, and that would make a nice short. So certainly, if anything comes to mind, I've had a few suggestions that have been helpful, as far as a couple of the segments that were turned into shorts. So certainly if there's anything out there that anyone thinks would be helpful as a TAIC short, we'd certainly appreciate if you could send us an email through the website contact form, and we'll make sure we get that out. So thank you.
Okay. Thank you, Patrick, for bringing that to us. And let's have one of those right now. Terry, you ready to queue up the one about the diverse data by Alex McConaughey?
I am. So,
Go ahead.
Okay.
So remember, guys, all our voices came through in the last video. So let's mute ourselves.
We're going mute.
Do that again. Let's go mute.
Let's mix and match. You need to mix and match when you have subs with diverse data. Diverse data comes from a number of things. You've taken pictures on different nights, different scopes. Maybe your camera was at a different rotation. Why do these things happen? Well, it could be because you goofed. And it could be because you are trying something different. But in either case, you need to mix and match. This is one of the top 20 questions on cloudy nights. Now, it gets asked in different ways. Here's 1 week's worth. And the questions were asked: how do I combine images with different camera settings, different temp and set points? How do I handle multi-session processing? What's the most economical and effective way to stack? And how do I use a mono for detail with a DSLR for color? Why do we need this? Well, here's an example from Stephen Curran. And Stephen, thank you for letting me use your picture here as an example. Notice he took a picture on successive nights, but his camera was at a slightly different rotation each night. And he wants to know, what can he do about it? Well, for one thing, he can get a darn good picture out of that data if he stays calm and just uses it appropriately. But all of these issues are related to the fact that they are using diverse data. And the solution when you're using diverse data is in the calibration and the registration. Calibration corrects for defects in deficiencies and equipment. It does that with 3 types of calibration images. Your biases in dark correct for errors in the camera, temperature differences, gain or ISO differences, and hot and cold pixels. And your optics are corrected by flats. These include vignetting and dust spots. And it's really easy to remember what to do in these cases if you have multi-sessions. You calibrate your light frames with calibration frames that match directly. That's simple enough to remember. What does it mean? Well, for biases and darks, there's some questions that are always getting asked. Yes, they can be taken at a different time. They don't need to be taken the night of the exposures of the lights. They're reusable for a while. You need to match the temperature and gain. And you need to match the time of exposure for darks. Now, there is some scaling involved, and you might not need biases for your particular rig, but this in general is good advice to follow. As far as correcting for the optics with flats, then you need it at close to the same focus. Often it's asked, do I have to be precise? Well, even during the night, your focus changes a little bit. So you need to get as close as you can, but don't obsess over it. It should be at the same rotation in the optical tube, and you need to have matching filters. If your filter has rotated at all, you must take new exposures. If nothing has moved, you can reuse flats for multiple nights. You're at a star party for 4 or 5 nights, one set of flats will do as long as you don't move your camera. The important thing to remember is that calibration frames must match your light frames no matter what session you took them in. Now, what happens if you can't do that? If you can't match it precisely, well, try to recreate it. Put your rig back together the same way it was, same rotation as much as possible, and take the pictures again for your flats. Or just fake it. Do the best you can, and maybe you're stuck with a paintbrush in Photoshop taking out a dust bunny or something. But do the best you can with that. Registration is easy enough to explain. Here are 2 pictures of the North American Nebula, quite different. One taken with an ASI 071 on a Samyang 135, and 2 years before that, my Canon 6D on a NP 101 was taking some images. And this star is that star. This wall of the North America Nebula is this wall over here. So it's the same thing. I'm going to have to rotate, scale, and translate this picture to make them match. Rotation is pretty easy. You can see that I got 2 images here. I come up over in PixInsight, and various other programs can do the same thing. Change the geometry. So I just rotated 180 degrees, and now you can see that the orientation of this star to the North American Nebula itself is the same in both pictures. Going on to scale, scale is adjusting something for size. I want to use part of this and part of that, so I need to get them matched approximately in size. By the way, this is not how I would actually do it, using the zoom factors on the screen and things like this. But for illustration purposes, this is what scaling is, making the one picture match approximately the same size as the other picture. And you can see when I've done that, the 2 North American nebulas are about the same size. Translation is also very simple. You can move your one picture up and down in relation, or left and right in relation to the other one. That's translation. Now, in fact, it's not done by moving things around with your cursor. But before we go too far down that road, I want you to remember registration is a standard procedure. You use it in all of your imaging. When you're binning, before and after meridian flips, when you're dithering. These are things you do on every session, not just diverse data. And so you're comfortable using registration. You use it every time you process. Mosaics, you have to use them in order to line up the various panels of the mosaic. If you have different image scales, different fields of view, or different optics because you've goofed or you've tried an experiment, you still have to use registration. You use it all the time. I want to use this North American Nebula and register it with this one so I can use the 2 pictures together. I don't need all of this area here, and I don't absolutely have to do this, but I'm going to first crop out a bunch of stuff I don't want in this image. So I open up my dynamic crop to PixInsight, and you can do whatever you want to do in your own processing program to do the same thing. And you know how to crop, so I'm not going to show you that. Take that time, just get it out of the way. I've already done it for you here. Get this into that. The way I do that is with my star alignment, which is what PixInsight calls registration. And I choose this from my reference frame. I choose that for the frame that I'm going to be registering. And now I put them together, and with a bunch of whirring and clanging and stuff like that. It takes a few seconds to produce an image after rotating, scaling, and translating. And you can see that, well, you can't see anything yet, so let's make it a little bit brighter by pushing up over here on the radioactive button, and it'll give me a screen function. And you can see that these two images of the North American Nebula are now registered. There's still a problem up here where I don't have an area covered, and that's going to cause me a problem in the future. See the two images. You can see that right here we have that area that wasn't covered by anything over here. How is this going to cause us a problem? Look at Stephen's image. See here? Over here? And Stephen was asking, how do I get this so that I can, how do I cure this problem? Well, it's very difficult to cure this problem. Unless you're a genius processor, you're not going to get this particular chunk over here to match that, to match this, to match that. They've just got different numbers of subframes supporting each of these areas. But with the creative use of cropping and further processing, you can get yourself a real nice picture. So don't give up, don't throw out any pixels. In order to avoid these problems in the first place, it's best if you do in-camera registration. It's best always if you have the same target and rotation. And here are 4 things to think about how to get it. One is you can use centering with plate solving. You just get the coordinates and the rotation for what you want, and you tell your plate solver to get it there. SGP, Nina, Voyager, they all do it. Coordinates, rotation from other images is where you can get your coordinates and rotations. You either look in the FITS header, and I'll show you that in a minute, or you can take an image and plate solve it and get the central coordinates and perhaps the rotation. Take a minute to do that, and then go ahead and use your go-to to get there. Take a few test exposures. If you've already gotten images on a different night in a previous session, go ahead and use the target parameters from that earlier run, from your earlier target definition, as you see here in Sequence Generator Pro. Then, if you don't have any of those facilities available to you, you're just using a sky tracker on a tripod or something, go to where you think you're supposed to take the picture, take a test image, and see if you've got it. If you don't, adjust a little bit and take another image. Iteratively keep taking your pictures until you've got pictures that match as well as you possibly can. That's what you need to do to get in-camera registration. Here I promised I would show you a FITS header. Here's a hamburger galaxy, and the FITS header, a little small to read, so I blew it up over here. You've got your right ascension and your declination marked here. You've also got the camera angle, 90.32, and so you can match it in your plate solver so that you can get the same image again. Also, it's wise to set the same exposure and set temp. Now, maybe you goofed and you didn't do this, but this is what you should do if you can get it right in the first place. And all this information can be found in your FITS header. But beware that you'll still get variations based on seeing conditions, observing conditions, and things like that. So this hasn't solved all your problems. You're still going to get some diverse data. You handle that with normalization or linear fit, which is a type of normalization. And the whole idea is that you can take pictures on various nights, and you can see we've got 300 seconds and 600 second exposures, and they're going to look differently depending on depending on the amount of exposure they've got. Well, normalization makes it so that all of the backgrounds have the same values, and this is one of the things you might need to use in order to regularize your data. I mentioned before cropping. You can see how it's very hard to get this whole image. You can't get the background anymore, but at least you can still get a real nice image. Now, there's some questions that arise about stacking. In particular, should I stack everything together, or should I stack them separately by each night, or what should I do? What stacking does is it rejects the outliers, then averages the rest. It lines up the values for all of the different subframes in an array. And then it picks the highest of those and the lowest of those, the ones that are really so far out of the range of everything else that they can't be real, and it throws them out. And then it averages the rest. And with all averages, the more you have samples, the more samples you have, the better the average is going to be. Now, there are exceptions to this rule. If, for instance, you've taken 1,000 subframes, it takes a computer a long time to do this with 1,000 subframes. So you may want to break that down into a smaller subsets. But best if you can do it all at once and calibrate all at the same time, and stack rather all at the same time. So the important thing to do when you're stacking is to calibrate your matching lights and calibration frames. Always match your calibration frames to your lights. Debar the one-shot color and use your sharpest reference frame for one registration run if you can. Integrate them all together into one master per filter. Okay, if it's a one-shot color, obviously it's just one master. If it's LRGB, HA, O3, whatever, then you'll need a stack for each of the different filters. And then you continue your processing. So always use one stack if you can get away with it. Not all diverse data stems from a goof of some kind. Sometimes you want to do something different. For instance, many people use a one-shot color to get their RGB and get their luminance from a mono camera. In order to do that, you have to calibrate your matching lights with your calibration frames, as always. Debar your one-shot color if you've got it, and then use one, and it's the sharpest luminance you've got, one reference frame for one registration with all of the subframes, whether they're one-shot color or luminance. And then integrate your one-shot colors into a master OSC and integrate your monos into a master luminance. Now you combine them as you would with any LRGB processing. So we have a number of different ways to ask the same question. It's a question about how do I handle diverse data? And the solution is pretty much the same: calibration and registration. If you understand these two concepts and how they work, that and a little bit of cropping, perhaps a little bit of normalization, and you've pretty much got the idea of what you need to do. So if you ever find yourself in a situation where you have subs taken on different nights with different rotations and all that stuff, you know what to do. Calibrate it, register it, adjust for maybe some normalization if needed, and just carry on as normal. Thank you.
Okay, thank you for that, Alex. We're back into the meeting room again.
Hi. I had to move because I was running out of battery, and I see that Jane asked on linear fit which one we choose as a reference, highest, lowest, or medium. I don't do it that much. I prefer to use the background neutralization and take it from there after the combine. But generally speaking, people go with the highest, I believe. And I'm sure there are others out there that can answer better than I can on that. Okay? And, oh yeah, I'm still the host, aren't I? And now Eric is going to take over, and Eric is going to take us off to the James Webb Space Telescope in Eta Corena. Go ahead, Eric.
Thanks, Alex. So, no matter how good your data is or what your sources are, and I certainly have my fair share, like terabytes of data, it's always interesting, pardon me while I arrange things, to be able to get data from some of these big telescopes or the space telescopes And when James Webb got up there and they started putting out these pictures, I wanted that data. And I wasn't alone. I think Tim Hutchison wanted that data too. So we all dug down and we got it. And then we just spent hours and hours and hours figuring out how to generate the image primarily of the Carina Nebula. And eventually, I sent an email off to Joe DiPasquale. I think he was on the show one time, and he's a primary imager out there. And he explained to me that what we were doing was maybe a little more complicated than it have to be. And there was a much simpler way to do it. And I'm going to try to generate an image from the data in 10 minutes. Now, I got a little more time than that, and I'm going to give an introduction. But that's the idea, to see how quickly we can generate an image from the data from the James Webb Space Telescope. Now, the first thing you have to do is, I have a couple of links. I'm going to copy those links and put them in the chat because you're going to need those. Let me go over here to the YouTube chat. Now, these are going to come over in real time, so they're probably going to come over before you actually hear me, but I think, did they come over? Hey guys, could one of the people take from our chat and make sure that these two links come over into the YouTube chat? Because they're going to need it. So if I can start.
Your link has appeared on the chat.
But
thread,
there's actually two links. There's two
okay.
links, and I think only one of them got here. Can you take them from our chat? There's two links from
I'll do that.
The Space Telescope. Okay, so I'm going to start sharing my screen. Present now. An entire screen. And let's present this screen. Share. Okay, I think I'm presenting now. So all the data from the space telescopes, from the big telescopes on Earth, anything that's financed by the government is available to all of us. It's free. You can download the raw data, you can download the stacked data, you can download the images. It's all in this MAST or the Minkowski archive. And if you haven't been there before and you want to start poking around, this is a good place to start. And all you have to do is simply enter your target. And here I entered Carina Nebula, and I'm going to do a search. And it's going to think for a while, and it's going to generate a list of all the data that's available to the Carina Nebula. And you can see there's quite a bit of it. But we only want the thing from the James Webb Space Telescope. So over on the left, I don't know if you can't see this, you could bring this up on your own computer. You could look at the mission. And there it is, James Webb Space Telescope. And when I click on that, then it brings up only the ones from the James Webb Space Telescope. So now we're down to a workable number. And I'm going to move this over so we can see exactly where we are in the sky. And zoom out a little bit. So when you look at the Carina Nebula, this is what you normally see, some version of this, if you live in the Southern Hemisphere. But what James Webb was just looked at a very, very tiny portion of it. And you see it kind of up here on the upper right of Carina Nebula. So if you zoom in on this, I'll zoom in, you can see the area where they generated data and they published an image. And now it's going to look a little more familiar to what they actually published. So now we see that little arc. I'm not sure what they call it, but that's the area that they generate data and publish an image. And if you want that data, there's a little box around it. And if you click on that box, now we see on the left-hand side, this is the 6 filters they use to generate that data. And if you click on any one of them, I'm not going to download them here because I've downloaded them earlier, but if you click on one of these, click. It will think for a moment. And in the lower left, if you can see it, it is downloading that data. And if you click on all 6 of them, you will have all the data for the Carina Nebula that they used to generate the image that they published, probably the first image that came out of James Webb. So that's how you get the data. So what is it you're going to get? So we're going to let this do its thing. In fact, why don't I just stop this since I already have this data? You're going to get the data from 6 far infrared filters that they use in James Webb. Remember, it is an infrared telescope looking back into the past. We all know about that. There is nothing in the visual range. So ultimately, we're going to have to process this and put it in the visual range. And that's kind of what I'm talking about this evening. So what are we going to get? On this tab over here, so these are the filters. These are some of the filters that we're downloading for this particular image. And I think we downloaded 90, 150, 200. So it's like 1, 2, 3, 4. I think these are the 6 filters that were downloaded. And you notice that they have colors, even though they're all infrared. And the reason they're illustrating them in colors is because that's how we're going to map them. That means that we're going to get the shortest wavelengths, and we're going to call those blue, even though we know it's far infrared, it's nothing we can see. And conversely, we're going to take the longest wavelength, is 444, and we're going to map it to the redder colors. And that's how all the data is handled from the James Webb. That is, they map it from the shortest wavelength to the longest wavelength. At least they did it for the Carina Nebula. And so that's what I'm going to do now. So I'm going to bring up Photoshop. And the reason I'm going to bring up Photoshop, if we can get it up here, Photoshop. There we go. So I took that downloaded data, and you can see that I processed it a few times just for fun. In fact, I probably processed it about 10 times, because each time you process it, it comes out a little bit different. The sky is, or the proposed sky is not blue, maybe a little more purple, or that the nebula itself is a little more or less orange, but it still comes out, no matter how you process it, kind of what they published. So you've downloaded the data from James Webb, from the Minkowski archive, from the MAST archive. You've taken it in the PixInsight. You've stretched it, and I just use a default stretch. I cropped a little bit of the edges so that, you know, the non-overlapped areas were eliminated. And I ended up with 6 TIFF images that I'm going to bring into Photoshop. Now, I'll use the magnifier where I can, or maybe if I ask Terry, then he'll do this for me. So I'm going to do something under File. Let's see, Scripts, Load File into Stack. If you've used Photoshop and you can't quite read this text, it's File, Scripts, Load Files into Stack. Oh, by the way, anyone want to keep track of my 10 minutes? Let's wait until I actually bring them into Photoshop and then start timing. So let me see if I can do it in 10 minutes. Load files into stacks. I'm going to browse. I've already got them lined up. And here we have the 6 filters. And if you can't read the notation, so here is the 90W filter. That is the shortest. And the longest one here is the 470. So these are the 6 filters. They're in TIFF format. They're default stretched in Photoshop. And I'm going to load them into a stack. And click OK. And so what I'm going to end up with, on the right-hand side, you see we have the layers palette. And I'm going to end up with a file with 6 layers. And if you didn't notice when I opened those up, they were labeled 1 through 6. And the reason I labeled them 1 through 6 on the left is so that when they were sorted from the shortest wavelength to the longest wavelength. Had I not done that, they would have been sorted alphabetically. So I just put 1 for the shortest, 2 for the next one, 3, 4, 5, and 6. And when they come into Photoshop, they're going to line up. I think they're going to start with, let's see. They're going to start 1, 2, 3, 4, 5, 6 when they all come in. And I'm going to have a stack of the 6 filters taken from the James Webb Space Telescope and default stretched in PixInsight and then saved as TIFF. So it's going to take us just a moment. We're up to 4. And so the question is, what am I going to do next with this? How am I going to process this into an image? Now, when I initially did it, I said, okay, I'm going to kind of take, the rainbow colors, and I'm going to assign each one a special color, and then I'm going to map them into Photoshop in an image. And that took a long time. Tim Hutchison came up with a more clever way, but it basically was the same thing. We're going to map the shortest one into the deep blue and the longest one into the deep red, and all the other ones kind of in between. But we're going to do it differently. Now, if you want to start timing it, now would be a good time to time it. So click, I have a stopwatch here. I'm going to see if I can do this in 10 minutes. Okay, ready, set, go. I'll put my watch up here. So we now have our 6 images, and I'm going to unselect it so you can see each one. This is the longest wavelength, and they're progressively shorter and bluer as far as mapping goes. So I'm going to take all of these and put them into a folder. And then I'm going to copy that folder, and I'll tell you why we're doing this in a second. So this is going to be my luminosity folder. Luminosity, saying, well, you don't have luminosity in this. But you want luminosity, because what you want to do is add these all up and use it as luminosity so that in the end, you have an image which gets rid of a lot of the artifacts. I don't know if you can see it, but some of these images have really funky star spikes, because every facet on that telescope, on every mirror, contributes to this a little diffraction spike of its own. Let me see if I can just zoom in and maybe see one of these funky spikes. Oh yeah, there they are. Look at those things. Because every facet of every mirror on the James Webb Space Telescopes generates a version of a diffraction spike. And we got to somehow get rid of those. So here's how I came up to get rid of it. I'm going to start with the base one, the shortest wavelength, and I'm going to add in all the others in a way which is called lightning. So when I click on this, I'm going to say, if any pixel in this image is lighter than the pixel below it, substitute it. If not, don't substitute it. And the way I do this is to select lightning as a way to merge these 2 layers. So each of these images, I'm going to put in and make it a lightning layer. Again, if there's a pixel in this image which is lighter than the pixel below it, substitute. And number 4, lightning layer. Number 5, lightning layer. Sorry, not normal, lightning layer. Number 6, lightning layer. And so now we have an image which represents an addition of all of these in a way using the lightning function within Photoshop. And then I'm going to select all these layers, and I'm going to say merge layers. And this is our luminosity. I'm hearing someone rattling Okay, so now this is our luminosity, and it is different than each one of the images. It is a summation of those 6 images using the lightning function. And by doing that, a lot of those irregularities in the star spikes are gone. Let me zoom in on it. Oh, I zoomed too far. Let's try again. Doesn't get rid of all the artifacts, but it gets rid of a good many of them. So it averages out those star spikes so you don't get those thousands of little artifacts in each of the star spikes. At least it works for me. So how am I doing? Oh, I'm going more slowly. I got to speed up if I'm going to do this in 10 minutes. All right, we're going to turn this off. So now let's go back to our 6 images below. So what Joe told me, instead of mapping each one of these images to a particular color in the visible spectrum, they just combined 2, 2, and 2 and made 1 R, 1 G, and 1 B, and that was the end of it. So that's what I'm going to do. And here's how I'm going to do it. We're going to unselect everything but the bottom 2, and I'm going to say take 50% of this one, and merge it with the one below. And since that's the longest wavelength, I'm going to call this, what color? We don't have an audience, but I think that's the longest one, so that should be red. Take these 2, make the upper one 50%. I'm sure there are other ways to do this, but this worked. I'm going to merge it with the one below it. And this now becomes our green. Let's see. And the shortest wavelength, make the top one 50%. So we're taking 50% of that one, merging with the one below it. Merge down. And of course, that is rename blue. We have our luminosity. We have our red, green, and blue layers. And we are almost done. How are we doing on time? Oh, 6 minutes. I think we're going to do it. All right, so let's take the blue layer. I'm going to mark it all. I'm going to copy it. I'm going to make a new document. I want a color document, not a grayscale. Create. And I paste it in my blue layer. And I go back, get my green layer, all copy, go to my RGB image, and now I'm going to select channels, and I'm going to put this into the green layer. It's green. Well, it's not actually green, but you know what I mean. I'm going to go back and get, what did I get? I'll get the red. I think I got blue first. Mark all, copy, go to my color layer, go to my channels, and put in red. Wow, we're not quite there, but we're close. Look at that. We got kind of yellow orange down there and a blue sky. So let me go to the layers. I'm going to make a copy of this layer because I'm going to do a little adjustment of the histogram. I'm going to go up to image, adjustment, just bring up the levels. And over here, I'm going to, where is our channels navigation? Oh yeah, I want to look at the histogram. I'm going to try to balance this out a little bit, and you can see what's going to happen. The red, let's go, no data here. Bring this up a little bit. Oh, we're creeping up on this thing, aren't we? Red, green. Now, of course, when you get to this point, what you actually do is strictly up to you. And we're going to get rid of a little bit of the blue because I think it's a little high. We're getting darn close. Let's make a little more red in this. So now we've made it, I think we're almost there. One thing I'm going to do, I'm going to choose another color palette. I'm going to assign a profile, which I know is going to be a little bit brighter. Okay, wow, look at that. We are really close to what they published. But we also see all these little dark centers in the stars. I don't know if you can see them. Let me zoom in on that. And how are we going to get rid of those things? And you can see all these funky spikes where every facet of the mirror is representing these little dots and dashes. We don't want that. Now, what did we do before, which is going to help get rid of this? We made a luminosity layer. So let me go back and get that. Where's our layers palette? Here's our luminosity. Let me copy that. Let's go back and paste that in. You know, it's luminosity. Call it luminosity. Look at that. We're almost there. One thing I do want to do, I'm just going to darken this up a little bit. Let me give it a little more drama. And, well, how much time is it? Gosh, darn it, 10 minutes and 50 seconds. Oh, I thought I could do it faster than that. So basically, once you get the data from James Webb, you download it, you bring it into PixInsight, you do a default stretch, you crop it a little bit so it's all registered. And if you bring it into Photoshop, and I'm sure there's a way of doing this in PixInsight, which is more or less the same, you can generate an image which is approximately the same as the one they published. In fact, in some ways, I don't think they really got this little red guy here quite as dramatically. And most of the artifacts, not all of them, some of them still need a little touch up, are not there anymore. So that is James Webb Space Telescope Carina Nebula in 10 minutes. Were any questions that came up along the way? Because I didn't stretch very much, but I think we've demonstrated it. I see a couple of questions. Go ahead.
Yeah, there were a couple of questions. One of them you spoke to a bit, but it was a question about the, Marcia asked, what was the advantage of using Photoshop over PixInsight? You did mention that you thought you could theoretically do it in PixInsight as well, but I don't know about 10 minutes.
The advantage is 30 years of experience with Photoshop. And I don't mean to be glib about that, but I have been using Photoshop since, actually, I think it's 29 years. I don't want to exaggerate, but I've been using Photoshop since version 1. I'm sure there's a way of doing this, basically to create the same kind of thing of combining images. You could do it by pixel math, put them together, do a combination by adding everything together in some way and coming up with luminosity and come up with the same result. It's just that I have more experience with Photoshop. And when I talk to the people at the Space Telescope Science Institute, that's what they said they did. So I just followed their lead.
They said they were using Photoshop as well?
Yeah, I know Joe uses Photoshop. I think they use a combination. I think a lot of the processing is done in PixInsight or their own software, but I think all the finished images. By the way, there's one other thing, and let me show you a real cheat, and I know they do this, and please don't tell anyone else that I told you this. So
it'll just be our secret.
Yeah, will just be our secret. If you take this image and you blur it, it looks better and gets rid of a lot of the nonsense in it, a lot of those artifacts. I would never tell anyone to blur an image, but somehow it does make it look a little bit better because you still have some of these artifacts in here. But if you, again, I'm just going to take, oh, why does it do that? All that experience and it still does things I don't understand. I'm going to take the luminosity. All right, click, click. Make a copy of it. And if I just, I'm hearing a lot of rattling around on the other end. So if I just take this, filter, blur, Gaussian blur, and blur this 2 pixels. This is a big image, by the way. It's like, I don't know, 9,000 pixels. Now, somehow things look better. No, it's still blurring. Blurred. Now, I'm not recommending this, but I know and I heard that some of the images they published actually get blurred a little bit because they look better. Again, all the images they publish with the space from the Space Telescope Science Institute, they're for the public. The science is done on the base images. It's not done on the published images. Just the published images kind of illustrate a lot. I see there was another, what is causing the black dot? Oh, they're too bright. And it just, we asked that question. It just runs over. It just reaches the limit. So the easiest way to do it is just to make them black. I can tell you a very clever solution to the black dot issue. Actually, adding them all together takes care of it. But I know that there's a black dot down here. So again, don't tell anyone I ever did this. If we take, if you want to close your eyes, you can. I'm sorry. I don't mean to joke about this. Is serious business. Oh no, I'm sorry. It's not serious business. It is fun business. I just take a little paintbrush. Oh no, don't do that.
I thought maybe you were going for the healing brush or something, spot healing brush.
I just messed up the image. There's black dot gone. What did I do? I made a big glitch in my image.
You just painted white right on that.
Yeah, I just painted white, black dot gone. And there were a few black dots that didn't get taken care of by making the luminosity. Black dot gone. Let me zoom back out. Yes, we wondered about the black dots. Stars are too bright, and so it just cuts off and it just registers as black. No information. Any questions? Everyone has the link so they can go and download any of this data. You can get any of the images from James Webb. You can get any of the images from the Hubble Space Telescope. You can get any images from almost any of the telescopes that you want to and download them. It's like any database. It takes a little getting used to find where everything is. But other than that, it's public data financed by the government, and any of us can use it no matter where in the world we are. Any more questions about this? Oh, you want to see what the actual image looked like? I think I have it here somewhere. What they published.
Eric, while you're looking for that, I want to point out that Bob Gendler has, I've seen several presentations from him where he has downloaded information from various telescopes and done just what you're just talking about. And the reason I bring it up is because that is an example of diverse data. The very kinds of things I was talking about earlier in the tutorial is you do have to register those things. You'll have to crop a lot of things. You'll have to normalize and all that other stuff. But you can take diverse data from various space telescopes, add it to your own, or add it to each other. You can do all that stuff with some of the stuff I was talking about earlier.
Yeah, and actually, by the way, I just brought up the actual published image. Their colors are a little deeper. So, I mean, if I really wanted to reproduce what they're doing, I suppose I could go back in here and yeah, their oranges are a little more orange. But again, at this point, you're just trying to make it fit your eye. And if you want your sky a little bluer, make it a little bluer. And if you want your nebula a little more orange, you can do that too. In fact, I can. Here's a little trick that I have in here. I think, let's see, tone mapping adjustment. I have a little. I just made it a little, well, it's thinking. Yeah, with everything going on. Is it done? Yeah, I made it a little more orange, a little more white, but that's a matter of taste. There is no right or wrong. They're just representing the data in some way by mapping it onto the color palette that we can see. And whether you do it my way or you do it 6 filters, you'll get a result which is very similar to what they publish. Can we stop sharing or is more people? There's another question. What is the typical download time and file size? I think the file size is like 250 meg, and I can download it each one in about less than a minute. So if we're done, I'm going to stop sharing.
Yeah, I think we got all the questions.
Okay.
Stop sharing this. And I almost did it in 10 minutes. Took me 10
Well,
minutes.
we were teasing Eric beforehand that it may take him longer to explain how to do something in 10 minutes. I mean, it may take him longer than 10 minutes to explain how to do something in 10 minutes, and that's a common thing.
Yeah, that's true. By the way, before we get derailed here, as far as mixing your data with a space telescope or a large telescope on the ground, I have done that numerous times, and it's a perfectly legitimate thing to do. And all you have to do is just put a reference in there. Hey, this is what I did. I took this data. And in fact, I got an APOD doing that by mixing data actually from Australia with some data from I can't remember, one of the space telescopes. And it was a different kind of representation of the data, and our APOD guys liked it. So please dig in there and make the best. This is something that we in the United States paid for. It's our data. Make the best of it. By the way, we can barely see you, Alex. You're kind of
no big deal.
either that or you're practicing for Halloween. I'm not sure.
I'm going for the spooky look.
Yeah.
I'm back outside. I've had to move around. We don't have real good internet out here, so I've had to move around a little bit just to be with you guys tonight. Are we about ready to wrap up, Eric? Everybody?
Yeah, unless there's some more questions.
Okay.
It looks about the right time.
I wanted to remind you that we will be here next week. Maybe I'll move back in where we've got some red light. We're going to be with Warwick. Warwick is going to be telling us 10 tips to get started in astro imaging. So please be back and join us. And sometime in the next, whenever we get around to it, Patrick will be turning what you saw tonight into TAIC shorts so that you can get the 14-minute and the more than 10-minute explanation of what you saw tonight in just that long a shot. Okay, so thanks everyone for being here tonight, and we'll see you next week.
Good night, everyone. Thanks for hanging out with us.
Terry's in charge tonight. Terry, thanks for hanging in there. There's a lot of weird stuff happening tonight, so thanks.
Okay. Thank you.
Take it away.